energy for working muscle, providing energy to the body, and focusing on neural and hormonal responses to starvation and exercise that kind of help mobilize and make fats available. And in our society, we talk about lipids, we talk about fats as being bad, and we're gonna spend a little bit of time on plate 135 just talking about one specific group of lipids, the cholesterols. So cholesterols have gotten a bit of a bad rap. Some of it's deserved, some of it's not. If we look at where cholesterols are used, do you recall talking about bile acids? Bile acids were composed of salts, and there was a huge cholesterol component to it. Cholesterol, in biochemistry, they're going to make you memorize the structural formula for cholesterols. You can see that they're compared to the carbohydrates, they're relatively large molecules, and certainly amino acids. So this is a type of lipid. It's structurally found in the plasma membrane. So we see cholesterol as being an important component of the plasma membrane. We also see it involved in bile acids, are steroid hormones, testosterone, estrogen, aldosterone, cortisol. Those all utilize cholesterol as building blocks. So in fact, cholesterol forms structural components more than it serves as a fuel. I think your notes say that cholesterol is not really used metabolically as a fuel, but it's important conserved for this. Now, I think one of the issues comes when you have too much cholesterol. Also, myelin was important in nerve conduction. Loss of myelin will produce a paralysis and death. Cholesterol is an important constituent of that. So where do we get cholesterols? We get it in dietary intake. So here are the lipids coming down in formation of. There's glycerol in the fats in the chylomicron. Some of these chylomicrons go to the adipose tissue, where we've talked about. Some of them are taken up by the liver, which we've also mentioned. And the conversion of these into cholesterols, into what are called low-density lipids. We have very low-density lipids, so these cholesterols then can form VLDLs. The VLDLs can be converted to low-density lipids, LDLs. LDLs can be converted to HDLs. This plays a critical role now in human medicine because LDLs, these are low-density lipids, cholesterol-based, tend to be associated with plaques. Well, all plaques are buildups on the walls of the blood vessels. So here, and in particularly the arteries, we talked about atherosclerosis. Atherosclerosis. Sclerosis means hardening, athero referring to the arteries. This hardening is due to plaque formation or buildup of material, primarily associated with LDLs. So this is where cholesterol gets a bad rap, and I think deservedly so. We see that cholesterol has important roles in building, but now we see that too much LDLs are associated with these plaques. When you go in and have your blood tested, one of the things they measure is they measure absolute concentrations of cholesterol. All right? So too much cholesterol means you have the potential to form lots of LDLs. So in addition to get a cholesterol reading, we see LDLs and HDLs. And you'll get this ratio. What you would like is you would like from a health standpoint, having more HDLs than LDLs, or having the ratio in the favor of the HDLs. HDLs are not associated with plaques, LDLs are. Heart attack, atherosclerosis, big issues, particularly in developed societies. Not as big issue if you're starving and have relatively access to fats. What about domestic animals? Well, we don't really appreciate a lot of atherosclerosis in our food animals. These are herbivores. They are not eating huge amounts of fat in their diet. So where you're going to see an issue with cholesterol, an issue with atherosclerosis, and heart disease are going to be in domestic animals that have access to large amounts of lipids. Dogs and cats. So we recognize this disease is becoming more and more prevalent in our companion animals, where the hypothalamus really drives you for lipid. I mean, we all like lipid. One of the neat things about ice cream is not just the sugar, but the butter, the fat, the lipid. And the hypothalamus is driven to stimulate eating in response to that fat. So one of my studies was I was trying to measure the energetics of lipid versus carbohydrate ingestion. We had rats. They're small and easy to measure their metabolism on. So we give them a diet. And what we wanted to do is we wanted to match the calories in the diet. So we gave them a carbohydrate-rich substance. And we used starch as the carbohydrate. And we found that unlike sugar, a simple sugar, we wanted something that was slowly metabolized, something that wasn't immediately taken up. We didn't want to push them into a glucose overload. So we gave them starch, and it was relatively non-palatable. And so they would eat a certain amount of that, and we would record it for that rat, measure its metabolic rate, then we'd bring it back the next day and we'd give it equal number of calories of fat. Well, the first thing was smaller volume of fat, right? It had more energy dense. It was important that we fed them the carbohydrate first, because if we fed them the fat, which consisted of 100% Crisco, essentially lard, these animals would consume 10 times the weight. Why? Tastes good, really driven for this energy. So if you think about evolution and animals trying to get adequate energy sources, particularly for omnivores and carnivores, they are really driven to eat that fat. Now in our developed society, we have access to way too much lipid, and that has led to problems. We see that in our domestic animals because they like fat. Plate 136. You are going to spend way more time talking about protein metabolism in a biochemistry class. Again, I kind of want you to have the big picture. We talked about amino acids binding together to form peptides and long chains, so part of the digestive process involved in the hydrolysis or breakdown of these peptides. No storage form for proteins. They are all structural component. And to remind you, where are these structural components? Muscle proteins. Certainly, 60-70% of our body, it may be made up in muscle tissue. Some of us more, some of us less. What is that? Actin and myosin. That is protein. Now, remember that most muscle is still water. 75% of your muscle is water. But the majority of the remaining component is protein. So structural elements of your muscles, connective tissue, collagen. talked about hemoglobin. Remember the protein, the important buffering properties of proteins. Hemoglobin in your blood. We also talked about antibodies or immunoglobulins. All of the enzymes in all of the cells, all protein. From your lab, you focused on blood components, the fibrinogen, the albumin that are present in the blood. Liver cell. The liver is involved, we've talked about its involvement in glycogen formation, glycogen breakdown. We also need to talk about, we talked about its role in fat metabolism. We also see it as a primary site of protein metabolism. Not only building up of proteins, but the breakdown of proteins. And so what I want you to know is in this deamination or breakdown of proteins in the liver, you produce ammonia. Ammonia is toxic, so in mammals, this ammonia is converted to urea. We talked about urea trapping in the kidneys, urea as a waste product. It's a waste product of protein metabolism. We also talked about how proteins can be broken down to make glucose. So I want you to remember that carbohydrates can be made up of structural components which are broken down in the liver. And here you see the release and the removal of urea by kidney. You see the use of the glycogen, or the glycogen gets broken down to glucose, and the glucose then feeds the nervous tissue, particularly during starvation. Hormonal controls. Growth hormone I want you to know about. Growth hormone is important in protein metabolism. Insulin, we talked about insulin. Androgens. Indirectly, we've made application to that. What do androgens do? Androgens are anabolic. They tend to build up. Steroid use in athletes makes them more muscular. Testosterone and androgens produced in a bull, much more muscling. So I want us to spend relatively little time on protein metabolism. You'll get more of that. I'm going to focus now on metabolism. And you're stuck with me because my PhD was on energetics. So we're going to spend a little more time on what's happening at the whole animal level. A byproduct of all metabolism is heat. In chemistry class, you may take a carbohydrate, you may take sugar, and you may burn it. So you put in oxygen, and you then measure a heat output from it. When you oxidize wood in the fireplace, heat is given off. Metabolism that occurs, so in the body you're not adding just oxygen and flames, you're taking the glucose and you're breaking it down. Each process in the breakdown of glucose liberates heat. And a mole of glucose that's taken all the way to CO2 and water liberates on something on the order of over 600 kcals of heat. What your body tries to do is capture some of that energy in the form of ATP and utilizes and stores glycogen and triglycerides for metabolism later on. So when we talk about our metabolism, we can be talking about our basal or resting metabolism and then our metabolism during exercise. I do want you to know that 1 calorie is defined as the amount of heat that is needed to raise 1 gram of water 1 degree centigrade. Okay, so that's kind of the classic memory memorization of the calorie. Most of you are familiar with caloric terms because when you buy food, you're looking at the calorie content. You know, how many calories does it have? That's an energy measurement, but it's also a measure of heat. So we oftentimes use metabolism and heat synonymously. It's true in part because as we metabolize, we produce heat. Some of the early measurements of animal metabolism were done on domestic animals. Why? Because it was very important in determining growth in these animals and what to feed them. The way that was measured was actually by measuring heat production. When I was in chemistry class, we measured the metabolism in a guinea pig by measuring heat production through direct calorimetry, a technique that was used in the 1700s to measure metabolism. So that is direct calorimetry. Direct calorimetry requires a room or a device or container that will actually measure the amount of heat produced. This is a true measurement of the amount of metabolism. Chemists like direct calorimetry. They want to know exactly how much energy is there. Nutritionists, they love to take nutrient items, put it in a bomb calorimeter, and measure directly the amount of heat. So when we talk about direct calorimetry, we're talking about the direct or absolute measurement of heat. It can be in a metabolic chamber or in a bomb calorimeter if you're a nutritionist. So up in animal vet science, lots of people that are interested in how much energy is found in this packet of food. My background is I want to know what is the metabolism of that organism. Won't do good to put that organism in a bomb calorimeter, blow them up and see how much heat they have in it. I'm interested in their metabolic rate. The technique for direct measurement of heat production, very detailed, very expensive. So the process we tend to use is indirect calorimetry. You're not measuring heat production directly, rather what you measure is oxygen consumption. Remember, for our equation for the oxidation of glucose, 6 C6H12O6 plus 6 oxygen goes to water and CO2 and heat. You maybe trap some of that heat energy in the form of ATP, but eventually you're going to use that ATP to pump ions to move your muscles. So this equation, which is all embraced by chemists, is happening in your body. Direct calorimetry measures the amount of heat production. Indirect calorimetry measures the amount of CO2 or amount of oxygen consumed. So implicit in this statement is indirect calorimetry only measures the aerobic component. For a cow on pasture, that's all you need to know. For a human running on a treadmill, jogging, virtually all of their energy metabolism is being supported by aerobic metabolism. Now, your quarter horse that runs as fast as it can for a quarter of a mile is going to use anaerobic metabolism. That is not going to be measured by indirect calorimetry. But very hard to get a room large enough to run a quarter horse, a quarter mile, and measure the amount of heat production. So it's kind of a trade-off. And what you find is the standard way of measuring animals' metabolism is by measurement of oxygen consumption. So how is oxygen consumption or metabolic rate influenced? Mass versus surface area. And note the units here are calories per day per kilogram of tissue. So you got this kilogram of tissue. And if it's a mouse, that kilogram of tissue, 200 calories per kilogram of tissue. Now, because it's a mouse, there's not a kilogram of tissue in the amount that's produced, and you don't have to know the exact numbers. All I want you to know is the trend. Small animals have a higher mass-specific oxygen consumption. That is, per kilogram, this number is higher. Compare it to a horse, which is 10. There's a 20-fold difference in the metabolism of a kilogram of mouse muscle compared to a horse muscle. Now, if you've ever cleaned up after mice, you know that it doesn't require shovels, but it does for a horse. So in terms of their overall metabolic rates, this mouse is consuming 4 calories during the day, the horse 5,000. So you have to feed the horse more. But on a mass-specific basis, much less per kilogram of tissue. As a comparative physiologist, this stuff kind of interests me just from general interest. As a veterinarian, this becomes important in determining drug metabolism. So if you're going to dose an animal, you need to dose it appropriately for its metabolic rate, because it is that metabolic rate that's going to determine elimination and metabolism of a drug. So blood flow to the kidney, kidney function, and liver metabolism, all going to be tied to the metabolic rate. Animals with very high metabolic rates are going to metabolize drugs much more rapidly, everything else being equal. So if you go into formulas and you start looking at drug concentrations, doses to be used, you will find that doses for laboratory animals much higher than for dogs and cats. So, and you don't have to remember these numbers, this is just as an example. In a cat, when I use ketamine IM, I'll give them 20 mg per kilogram. In my pigs, I'll use half the amount, 11 mg per kg. In rodents, I may dose them at 90 mg per kg. So higher mass, now, right, kilogram of tissue, you're not going to find a kilogram of mouse tissue. But what this tells you is the mass-specific metabolism much higher in a smaller animal. So I need to give it more drug per body mass. Activity. National Research Council, NRC, comes up with feeding your dog, feeding your cat, feeding your goat, feeding your horse, feeding your cow, based on activity levels. Is the horse sedate, standing on pasture? Is it a working horse? And is it working moderately or strenuously? You need to adjust nutrient inflow based on metabolic rates. Sports exercise physiologists are very interested in what's happening with exercising humans. They're looking at this end of the spectrum. You need to provide nutrient delivery to support that level of metabolic rate. Average consumption for your basic human, 2,000 calories a day. Those are big calories. 2,000 calories a day. You're going to do the Tour de France, more than 4 times that. Eating 9,000 calories a day is a challenge, even if you're eating Crisco or pure lard. Invariably, these cyclists lose weight because the metabolic rates are so incredibly high. Contrast that with, here's a professor, so sitting in front of the computer, very low activity levels, low metabolic rates. The fact that there's also a professor has this concept of age. Androgens affect more metabolically active tissue, more muscle. So males have higher metabolic rates than females. Females more lipid. Lipid has relatively little oxygen consumption to it. So they have a smaller mass-specific oxygen consumption. And then certainly in terms of age, we see that young individuals have higher metabolic rates than elder individuals. Probably not important in food animals because a lot of food animals disappear before they get too old. But domestic animals, companion animals like dogs and cats, it's all taken into account for you because what you do is you go to the market and you buy the bag of food for the young puppy, young kitten. When they get to ruse age, you buy them the sacks of mature food. That'd be great if they could do this for humans. You know, you'd have the little bags that you'd give for the kids, and then you'd have the old person's bag of tasteless, dry, no lipid, very low calorie, but lots of bulk that fill you up but don't provide a lot of calories. Eating. Food ingestion increases body temperature. The process of digestion, the process of absorption, the process of enzymatic conversion and storage of glycogen and production of fats all takes energy. So you find your metabolic rates go up after an ingestion of a meal. That's kind of the after the big Thanksgiving feast, you feel hot, flush. Well, your metabolic rate may have gone up 10%. Temperature is a function of, metabolism is a function of body temperature. We tend to regulate our body at a specific temperature. Some animals, like lizards, fish, don't. So their metabolic rate is going to be a function of their body temperature, which is oftentimes a function of the environment they're in. And their metabolic rate may change by on the order of 100-fold during the day because of temperature and activity influence. Mammals tend to regulate our body temperatures around 37 to 39 degrees Celsius. Metabolic rate increases 15% for each temperature, each degree centigrade increase. So if you're one of the consequences of exercising is your body temperature goes up. The payoff is, well, not only are you consuming more energy during the activity bout, but you have an elevated body temperature after the exercise. That elevation of body temperature will help burn more energy even after the exercise has been done. So this is kind of like the classic, you need to exercise because it's good for you. Not only is it good to help burn off calories, but it helps burn off calories even after you stop. This last one down here is the environmental temperature and climatic adaptation. You have a cow standing out in Colorado, in Durango in January. Metabolic demands are going to be higher. You need to feed that animal for that. So I want now to turn to plate 140. So we're going to skip a couple plates, and I'm going to end just talking about body temperature, heat production, and heat loss. So here's the animal's body. It has some core temperature. Humans regulate at 37 degrees centigrade. Our domestic animals a little higher. We have insulation. There is tissue which insulates this core from the external environment. We can modify, in humans, we modify this amount of insulation by eating a lot and getting bigger and fatter. We modify it by putting on a jacket. We modify it by taking off a jacket. Our domestic animals modify the amount of insulation primarily by changing the amount of pelage or fur on the outside of their body. Thicker coat in winter, more insulation. That helps to retain heat. More insulation also can dampen the amount of body temperature change increase. So we think about it as, putting on more insulation in the cold. That insulates the core from the external environment, so we tend not to lose as much heat. Insulation also works the other way around. If you have lots of insulation, you don't gain as much heat. Now that's a trade-off. So you have to think of insulation kind of working in both directions. Well, how is heat lost? How is heat gained? Radiation. We radiate heat based on temperature. So the temperature of our skin, the temperature of the environment that we're in. That has to do with electromagnetic radiation and the heat of the object, whether they be air molecules or skin. If the air molecules are very hot, we can gain heat through radiation. Some of this radiation is invisible, so perfect example. When it's hotter, I've got more electromagnetic radiation coming in. Sun goes down. It's night. You're standing out in the desert. Air temperature is cold. You radiate heat off. So radiation works in both ways. It's modified by the movement of the air, movement of the fluid, convection. If the air is cool, let's say it's 70 degrees, so let's say it's 20 degrees centigrade. Body temp's 37, outside's 20 degrees. You will tend to radiate heat off. Now what happens is the sun comes out, heats up the air temperature to 40 degrees centigrade. Air movement will dramatically influence your perception of that temperature. So if it's 40 degrees and the air moves over, you'll tend to heat up. If the air temperature is 10 degrees centigrade and it moves over, you'll tend to cool down. So like radiation, convection can influence whether you gain heat or lose heat. Conduction. Conduction is direct physical contact. So you sit down on a metal chair. If the metal chair is 0 degrees, you perceive that as cold, you lose heat to that. Hot dog on the tile. You see the dogs when they spread out on the tile, what are they doing? They're increasing the amount of physical contact between their body and a cool surface. That helps them lose heat by conduction. Lizards on a hot rock. They'll come out, press their body down. They will increase the conduction because what they want to do is they want to gain heat. So like radiation and convection, conduction can be either heat gain or heat loss. The final method of heat exchange is by evaporation. Evaporation only works to remove heat. So unlike convection, conduction, and radiation, evaporation only a means of heat loss. So how evaporative mechanisms, very important in regulating body temperature. Horses and humans, large amounts of sweat glands. They can lose a lot of heat by sweating. Dogs. The only sweat glands they have are in the foot pads. They're involved not in temperature regulation, but rather in scent delivery. So the way dogs maintain and utilize evaporation is through a panting mechanism. Remember talking way back when about anatomic dead space? Dogs move air in it, a small volume of air in and out of the pharynx and mouth region, buccal region, at a high frequency. Well, what is that doing? That's evaporating water. So that's kind of their mechanism for heat loss. So evaporation, only a mechanism for heat loss. Sensible perspiration or water loss, sweating and panting. The example they talk about is insensible, is water that's lost through the lungs. When you inhale, if you're out in La Quinta, it's dry desert, you inhale dry air. When you exhale, your exhaled water vapor 100% saturated. Dry air coming in, no water in it. When you exhale, you've taken that volume of air and you've saturated it with water. That is a form of heat loss. Horses, tremendous respiratory exchange while they're racing. About 30% of that, you don't have to remember that number, 30% of their heat loss is through evaporation from the lungs or insensible perspiration. So having both insensible perspiration and sweating and panting serve as mechanisms for maintaining body temperature constant. And I think with that, I'll finish there.